Hello and welcome to our TI Technology webinar hosted by Texas Instruments Australia. We are excited to bring you Sampling and Proportions, Unit 4, Topic 4 from the QCE Mathematical Methods course with a very experienced mathematics teacher, lecturer and TI Technology user, Mr. Peter Flynn. My name is John Bayman and I am your host for this event. I teach mathematics to years 7 to 12 students at Lachlan Catholic College in Darwin, where I use TI technology to help students make stronger connections in their understanding of mathematics. And before we get started, I just wanted to remind you of the QCE teacher resource books that are available on the TI Queensland website, which have been extremely popular. If you don't have a hard copy yet, please email teacher-support@list.ti.com and they'll post one out to you. Also, to let you know that the General Maths Teacher Resource Book will be available from the end of July, the end of this month, which is exciting. And as you can see, Peter was one of the main authors of these fantastic free resources. As a general reminder, tonight's webinar is being recorded and will be available to rewatch or share on our on-demand TI Australia website, as well as please feel free to send any questions at any time to Peter using the chat window on the right-hand side of the screen. So I'd now like to introduce our presenter this evening, Mr. Peter Flynn. Evening, Peter.
Yes, good evening.
It's great to have you with us. So as you can see, Peter has been a mathematics education teacher and lecturer for over 30 years in a variety of educational contexts. He has a rich knowledge of computer algebraic systems, as well as various examples. As I mentioned, he is also co-author of the TI's QCE teacher resource book. So plenty of knowledge and plenty of things for us to learn this evening. Peter, I can see your screen, your Inspire teacher software, so I'll pass over to you. Thank you.
Yeah, thanks very much, John. Good evening. So we're going to look at Unit 4, Sampling and Proportions. So I'm Peter. There's my email address. This file will be available to you at the conclusion of the webinar, and you can also send me an email if you ever want a question answered. So the outline for this evening, it's a bit busy. We'll see how we go. We want to look at sampling from a distribution. So we'll look at the binomial and the normal. We'll look at sample proportions as a random variable, look at confidence intervals for population proportions, and we'll look at sample sizes and margins of error. So the first example, we'll look at sampling from a binomial distribution. So let's think about a mythical situation where 30 students sit a test consisting of 25 multiple choice questions. Each multiple choice question has 4 alternatives, and each of the 30 students in this instance guess the answer to each multiple choice question. We can denote random variable capital X to be the number of correct answers or successes obtained by a student. Now we can simulate this by using a command in TI-nspire called the random binomial or ranbin command. So we're going to use it to first of all simulate this situation of 30 students guessing the answers to these 25 questions. We're going to determine the sample mean number of correct answers and compare it to the expected number of correct answers, which you should already glean is 6.25, 25 times a quarter. We're going to repeat part B for 100 students and then for 1,000 students. Have a look at the histogram for the 1,000 students simulation. So 25 multiple choice questions. So n is equal to 25. The probability of obtaining a correct answer or a success in each question is a quarter or 0.25. We're going to sort of look broadly at 30 students, 100 students, 1,000 students. We can also use a slider to adjust the number of students. Before we do so, it's a good idea whenever you're going to do a simulation to seed the TI-nspire. Now, I'm not going to enter my mobile phone number without the leading 0 here, but to seed the calculator, what you need to do is press Menu, 5 for probability, 4 for random, 6 for seed, and then choose some digits, 1, 2, 3, 6, 5, 8, something along those lines. Press enter. So the simulation is based on a pseudo-random generated set of numbers. So it just puts you in a position in the queue. If everybody used 1, 2, 3, 6, 5, 8, then everybody would get the same answer. So there are some times where that's an advantage. In this instance, it's not an advantage. So let's look at a list and spreadsheet page. It's an extremely busy page. First of all, in the column heading cell, the variable is correct, denotes the number of correct answers. In the formula cell, what I've done is I've entered a formula. Now, the random binomial command is found in the catalog. So all you would need to do is press catalog, then go to the R, so press R, and then scroll down and you'll find randbin, for example. Now, the syntax is N, which in this instance is the number of questions, P, which is the probability of success, which is based on the number of alternatives, and students. Okay. Now, notice that with N and P, there's a small sort of like apostrophe before the N and before the P. What that's denoting or telling us is that N and P are variable references. They're not column references, because further along in the spreadsheet, there is a column N and a column P. Now, if you wanted to enter those from scratch, there's a punctuation key here, and what you would do is press that and then scroll along and you can select that particular symbol. Right. So there's our syntax, and what we've been able to generate, well, I'll explain column B just in a moment, but what we can glean first of all is that student 1 got 10 correct answers, student 2 got 7 correct answers, student 3, 6 correct answers, etc., etc. Now, normally when you use the random binomial command, these would be numbers. So, for example, it might be 25, 0.25, 30. But I'm using these variables which are assigned in the spreadsheet, and you can see them because they're in the cells and these numbers are in bold. So first of all, click on cell B2, and using the assign command, which is accessed by pressing Control symbols template, you can assign N to be 25, and we can change that if we wanted to. We're assigning P, the probability of success, to be 0.25. And the one that we're really interested in here, because we're not going to change the number of questions and we're not going to change the probability, we're going to change the number of students. All right, so we've assigned the number of students to sit this test to be 30. In cell B1, I have typed in this command, which is saying, let's get a decimal answer for the approximate mean number of correct answers, and let's get that as a decimal. So approx is found in the catalog. So again, you'd press the catalog button and then press, say, for example, B if you wanted to, and then scroll up until you find approx. And this is saying that from this 30 students, the average number of correct answers was 6.93, or close to 7. And we can compare that to the theoretical value, which is obtained by, because we're dealing with a binomially distributed variable, the expected value E of X is equal to NP. N is 25 and P is 0.25. So we can compare 6.93 to 6.25. I won't go into column C and D too much, except to say that what I've done there is I've used the one variable statistics feature, and you can also see there that the sample mean, or from this sample, the mean number of correct answers is 6.93. Now, to access that, you would press menu, 4 for statistics, one or enter for stat calculations, and then perform one variable statistics. That should be, the menus are quite clear and you shouldn't have any dramas there. Okay. Next page here, we've got a data and statistics page. So if I press tab, and what we see there is the variable correct appear, and then press enter, what happens is we get a dot plot, and it illustrates that, for example, 2 students got 3 questions right, 1 student got 4 questions right, etc., etc. Okay. Now, what we can do is we can obtain a histogram as well, and we can use these settings to get a very nice histogram. The default plot is the dot plot. So if we press menu and then 1 or enter for plot type, 3 for histogram, here's the histogram. Now I'm going to, in open space, press a control menu, which on the computer is a right click, choose bin settings. I want an equal bin width. I want that to be 1. I want to press tab and have an alignment of 0.5. Press tab to highlight OK, and then press enter. Okay, so here's a histogram of the situation of our first simulation. Now, when we increase the number of students, what we'll need to do is we'll need to adjust the window. So let's go back to the spreadsheet, and the original question said we're going to start off with 30 students, then we're going to do it for 100 students, and then 1,000 students. So we go into the spreadsheet. Here's the cell where the number of students is assigned or defined. We'll change that to 100 and then press enter. And what happens is we get an updated list of how the students performed. We get an updated sample mean. So this one, for these students, the average number of correct answers is 6.11. And so it's a dynamic spreadsheet. So you change one of the assigned parameters, if you'd like to call it that, then you will get an updated set of results. So as you can see here, the window now is not fit for purpose. But if we press menu and then 5 for window zoom and then 2 for zoom data, here is our histogram for the 100 student situation, and you can run your cursor over here and we can see here, for example, that 18 students got 6 right, and that happens to be the mode. There's not much in it, between 5 correct, 6 correct, 7 correct, and 8 correct. Okay, let's go back now and change the number of students to 1,000. So we change it to 1,000, press enter. And what happens here is the average number of correct answers is 6.33 compared to the theoretical 6.25. As we increase the number of students, we would expect this value to get closer and closer to 6.25. And again, we go to our data and statistics page, and of course, at the moment, we haven't got a great window, so we press menu 5 for window zoom and 2 for zoom data. What you'll also notice, as we're increasing the number of students, the histogram, it's looking more and more like a normal distribution. There's greater symmetry appearing, and it's becoming more prominent that the mode is 6, and as I said, there's a nice symmetry starting to form. What we can also do is we can insert a slider. So I'm going to go back and just change this to 10. Just because of time purposes, this demo is slightly abridged. And we've still got this, press menu, window zoom, 2 for zoom data there. Okay, so what we can do now is we can press menu, 3 for actions, and 4 for insert slider. Our variable, if we can go down and find students, let's start off with 10. So I'm pressing tab to move through the various slider settings dialog box fields. Let's have a minimum of 10. We'll just have a maximum of 100 here. Step size 10. And we'll minimize the slider. Press OK. And then it's a matter of grab and move the slider. And what we can do now is there'll be some window adjustment required, but you can press on here and you can change the number of students. Okay, and so we'll need to adjust as we go along, but you can see that as you increase the number of students, we start to get, and we'll need a lot more students, and I can bang that up to 1,000 quite quickly again. We can see that the histogram is going to become more and more normal looking. The other thing we can do is we can also plot 2 vertical lines. So I might just do that now. So if I press menu and then go to 4 for analyze, 8 for plot value, the first vertical line is, and we can type this in using the keypad, is the sample mean, or the mean of the correct answers. So to find correct, the variable, press var, it's up the top there, press enter, and that is that vertical line that represents the average number of correct answers in the sample. You can also add a second vertical line, so menu, and then 4 for analyze, 8 for plot value. And in this second one, what we'll do is we'll put in n times p and press enter, and that will remain static at 6.25. Go into the slider settings, if I can, and go to the settings. And what we'll do is we'll just increase the maximum there up to 200. Go to OK. And what you can do is you can increase the number of students, and you can also watch the mean number of correct answers from the sample and watch that vertical line dance around the static vertical line, which represents the expected value of 6.25. So if I go to menu and then window settings here, we'll have Xmin, Xmax. Let's have Ymax say at 60. Hopefully that'll be good enough. Let's see. And now we click on, and what you'll see is the vertical line dancing around the static vertical line, and that's a good place to finish it. Actually, that looks really nice and symmetrical. It also gives a sense of randomness, of fluctuations, and you can also, if I take it back to 100, for example, you can also animate the simulation like so. Okay, so stop there. The other thing we can do in a calculator page is we can also determine the number of occurrences or the frequency of a particular outcome using a command called the COUNTIF command. And the COUNTIF command, that's also found in the catalogue. So if you press the catalogue, then maybe go to D and then scroll up down a bit. There's the COUNTIF command. You can also type it in on your keypad, no worries at all. So COUNTIF, and let's say we want to count the number who got 6 correct. So if we press variable correct and then comma 6 and then press enter, for the most recent simulation, that's telling us that 13 students in inverted commas got 6 correct out of those 25 questions. So I've explained the vertical line situation. I've also explained how to add a slider, and we don't need to show that again. So we'll go to our second example, and this is sampling from a normal distribution. And so random variable capital X is normally distributed with a mean of 100 and a standard deviation of 15. There's a similar command to the random binomial command called the random normal command. And we're going to use the randnorm command to generate a random sample of size 10 initially. And then we're going to generate a normal probability plot. Now, the normal probability plot, I think I'm directing this more to teachers than students here. We're going to repeat the above for random samples of size 30 and 100, so increasing the sample size. Look at what happens to the normal probability plot as the sample size increases, and for a random sample of size 100, plot the histogram, and then overlay it with a normal probability density function.
Peter?
So, not as busy, this spreadsheet. This time in the column A heading cell, the variable is called sample. In the column A formula cell, again, so randnorm can be found from the catalogue in the R's. And if you wanted to, you could have there as a mean of 100, standard deviation or sigma of 15, and n, which is the sample size, is 10. Notice that mu and sigma, they don't have that apostrophe there because there's no columns in the spreadsheet called mu and sigma. This apostrophe n is denoting a difference between variable n, which I've assigned here, and spreadsheet column n, which is off to the right there. So you're well within your rights to add numbers in here, but what I've done again is I have assigned mu. Now, I haven't used the Greek letter mu because that's a reserved variable symbol. So I've just used the word mu. So using the control symbols template for the assign command, I've assigned mu to be 100. I've assigned sigma to be 15. And I've assigned n to be 10. And so we've got a random sample of 10 numbers from the normal distribution with those parameters. Just while we're here, some shortcuts that you can use for the spreadsheet in terms of navigation. Control 1 takes you to the bottom. Control 7 takes you to the top. Control 3 takes you down a page. Control 9 takes you up a page. So there's some navigation hints for you. And also the other thing is if you wanted to perform the simulation again, if you press Control R, the R sort of stands for refresh, redo. So you can also do that. Okay. In this cell B4, I've just typed in the cell formula equals mean of sample. I wouldn't type in the sample. I'd use the word sample. I would use the variable p there. So our population mean's 100. Our sample mean is 101.956. And this is our standard deviation of the sample standard deviation. And notice that that's quite a bit different. It's 21.07 compared to 15. And we can suspect that that's because we've got a small sample size. To find either mean or sample standard deviation, if you press menu and then go to 3 for data and then 6 for list maths, there you'll find, for example, number 3 is the mean and number 7 is the sample standard deviation. Okay. So I put some of these pages in just so that I remind myself to make these remarks. So again, this is probably more for the teacher than the student. Everything I've done up until now is definitely for the teacher and the student, and the teacher demonstrating this to the students in class, and also if you wanted to, getting the students to set up these simulations for themselves and for them to compare results with each other. But I think I would just briefly, for your benefits here, describe what a normal probability plot is and what it does. And what it does is it helps assess whether or not a data set is approximately normally distributed. Now, data is plotted against a theoretical normal distribution in a way that the points on the plot should form an approximate straight line. The straighter the line, the more normal the distribution is, or in other words, more normal the sample from the distribution is. The more that the points depart from the straight line indicates a greater departure from normality. So on a data and statistics page, we're going to follow these instructions. We'll get a normal probability plot for a sample size of 10, and then go back and get one for 30 and one for 100, and you should be able to see something quite interesting happen. So on a data and statistics page, we will enter sample like so. So again, our default plot is the dot plot. We press menu and number 1 or enter for plot type, and then 4 for normal probability plot. Okay, so there we get sample. So these are our random sample 10 values plotted against an expected Z value. And you can see there that the sample mean is listed and the sample standard deviation is listed. So it's if you like, linearizing the data. And it's not too bad. What you often see in these probability plots is the departures seem to occur more at the ends more than the center, but that's pretty, that's pretty reasonable. We'd expect a better fit when we come to increase the sample size. So we go back to our live spreadsheet and we'll change N to be 30. We'll notice that the sample standard deviation is closer to the population standard deviation, which is what we expect. And the sample mean is around about the population mean. We should get an update on our normal probability plot. And what we see there is it's seemingly a better fit, a little bit off here. And what we'll do now is we'll go back and we'll change the sample size to 100. As we do this, right, so we're getting now a sample mean that's quite close to the population mean, and the sample standard deviation is not too far away from the population standard deviation. So we've got statistics, sample statistics, and we've got population parameters. So if we go to our normal probability plot, that's looking really nice. So what the normal probability plot is showing you is as you increase the sample size, you're getting more and more normality. You're getting closer to a normal distribution. So I think while I'd be a little bit reluctant to show the students, you might and give it a go and see what happens. This is more for your benefit. If you've got quite a bright class, by all means, bright students in your class, by all means, give that a go. So what we can also do is we can press menu, plot type histogram, and we can set up our histogram and we can adjust our window using those following settings. And we can also overlay a normal PDF over the top. So we'll come to here, sample, and then what we can do, we can press menu, plot type, and then go to histogram, like so. That looks all right. Equal bin width. So we might make a bin width of 10. Alignment, maybe 55, not sure. See how we go. Okay. Press menu, window zoom, zoom data. Okay. So what we could do here is we could also set up a slider and increase the value of n. So we just need to make sure where we're at. Go back here, change that to say 10. Come back to our histogram here, and we can also add vertical lines as well to represent the population mean and the sample mean in the same way, and watch the sample mean dance around. We can also do that. But for the purposes of this, we'll just go menu, 3 for actions, 4 for insert slider. Now what we'll do is the variable is we'll just change n. You can change the mean, the standard deviation, whatever you like here. Value of 10, minimum of 10, maximum of say 100, step size of 10. I would make these more dramatic and increase the sizes here, but just for the purposes of tonight and purposes of changing the window, I'm keeping it quite constrained. Right, so here's now if we increase the sample size, what's happening there? I mean, we might just change that to say 200. And I might take a punt at the window. So say 60. You can always adjust. Right, so as we increase, it becomes more and more normal. So that's franking what we saw with the normal probability plot, where the symmetry is increasing there. We could also have the 2 vertical lines, but we can also plot a normal PDF, a normal probability density function, as an overlay. So we can press menu, 4 for analyze, and then number 9, show normal PDF. And there we've got the normal PDF. Now there, That's the sample mean, sample standard deviation there. So it just gives a nice fit, as you can see there. Okay. I think that's everything to do with the sampling from those two distributions. So let's move on to the next demonstration. It's the last demonstration really before we do sort of two questions, but we do it not in a calculator application, but in a notes application. So let's have a look at sample proportions as a random variable. So we'll assume that 67% of people in Queensland have brown eyes. So we're going to generate the distribution of sample proportions when samples of size 10 are randomly selected from the population. These questions, we do have to do them in a slightly backhanded ways. We have to assume a p-value. We have to assume a population proportion, which is not what happens in reality. We want to display the distribution on a dot plot and on a histogram, and then comment on the distribution generated. Repeat part A for 200 samples of size 30. All right, so with 200 samples each time, increasing the sample size from n equals 10, n equals 30. Display the distribution on a dot plot and on a histogram. What do you notice when the sample size is increased? You can explore how changing the sample size or the population proportion or the number of samples affects the distribution of sample proportions. So again, this is a busy, live, interactive spreadsheet. In the column A heading cell, there is the symbol for the sample proportion p hat. You can use p hat. So if you press catalog, go to number 4, and then go for a bit of a hunt, you can find small p with circumflex, which is p hat. So it's good. We can actually use the same notation in TI-nspire as what we do teaching and learning and working mathematically in this area. Now, for a sample proportion, what we have to do is we have to divide by the sample size. So we've met these commands before. From the catalog, you find approx, which is short for approximate. From the catalog, you find random binomial, randbin. Notice the N, the P, and the S, they all have that apostrophe, and you're hopefully starting to get the gist of it, that N, P, and S are assigned in the spreadsheet. And just make sure you're dividing. To get P hat, you've got to divide by the sample size. So in other words, we're going to get proportions between 0 and 1. So jumping the gun a little bit, this is 0.7, for example. So n equals 10. So I've assigned n to be 10. Assigned p to be 0.67 and assigned s to be 200. Now, our population proportion p is 0.67. You can calculate the mean of the sample proportions, and it's 0.674, which is really close to 0.67. You can also compare the population parameter, the square root of p times 1 minus p on n, with the standard deviation of the sample proportions, and again, it's really close. So what we're showing here, and if I even went back and press Control R, for example, the sample proportion is a random variable whose value varies between samples. So that's a very important concept to get across. The distribution for this can be displayed on a data and statistics page. For small sample sizes, we're likely to, or we expect to see a skewed or negative distribution resulting because the P, the population proportion that we've assumed, is not 0.5, it's 0.67. So hence we expect to see a skew. We wouldn't expect to see many samples to have no people with brown eyes or only 1 to 2 people with brown eyes. So back here, for example, the sample proportion is 0.4. So in this sample, 4 people had brown eyes. In this sample, 8 people had brown eyes. So we've got a data and statistics page. And what we do now is we get a dot plot, and we can see it's not unexpected that the distribution is largely centered around, and it's that negative skew we were talking about, 0.6, 0.7, 0.8. The mode is 0.7. And note that we got one, and this is really good it's good to mention the extremities. We had one sample where only two people had brown eyes, and we had one sample where all 10 had brown or have brown eyes. All right, so this is really illustrating this idea of a random variable, of fluctuation, of randomness. And so when teaching these concepts, it's so important to embed simulations into your teaching and learning. So you would expect, but not necessarily obtain, a distribution centered roughly around 0.7. So now we're going to follow the instructions to get a histogram. So let's get a histogram. And we're going to fit a normal curve over the top. So here's this again. Press menu. It's nice watching the dots move. Press menu, 1 or enter for plot type. Then 3 for histogram. And so control menu or right click, bin settings, go for a width of 0.1. Just check and see what this alignment's like. Okay, seems reasonable. I think, yep. Okay. So the other thing we want to do, or could do, is fit a normal curve to the distribution. Okay, so we can press menu, 4 for analyze, 9 for show normal PDF. Okay, so we've done that. If we press menu, 4 for analyze, you can. It's like a top. It's a toggle. It's a hide and show. You can also hide the normal PDF as well. So we can go back and we can repeat part A with a larger sample size, n equals 30. So we can go back to the spreadsheet. Could also have set up for us a slider. So we'll change n to be 30. And therefore you get an update on your sample proportions. The mean of the sample proportions, again, is quite close to the population proportion. And we're also very close in terms of the population standard deviation and the sample standard deviation for the proportions. And also what you'll notice just on the way through there, if we get to the one that I'm interested in, or go back to this one, what you'll also notice actually is you'll notice a scrunching of the dot plot. So it's narrower. It's still centered around, you've got a mode there, probably 0.65 or 2/3, whatever it is there. It will be 2/3, with 0.7 quite close. But notice that as you increase the sample size, what happens is the distribution is narrowing, it's scrunching up. And you can see that because in your formula, you've got a square root, and inside the square root, you've got n as a denominator. So you increase n, and that's the role that's playing there. So menu, and then 5 for window zoom, 2 for zoom data. Okay. So that's the situation for 30. So as the sample size increases, the distribution becomes more and more symmetric and more closely centered around 0.7. You can examine the distribution of sample proportions more closely. You can repeat the random sampling. You can change the values of P, the population proportion. You can change the values of N. You can insert a slider. So I might go back here and just insert a slider in here. So menu, 3 for actions, 4 for insert slider. And we'll change the value of N. We'll put it back to 10 value, minimum 10. We'll go up to, let's say, 80 in steps of 5. Okay, so we'll put that over here. And look what happens. All right, we've got this lovely scrunching of the distribution. If we change the settings and we increase the maximum there to say 200, it's a bit overkill, but still. There we go. And of course, you can animate. Okay. So what's going on? As the sample size increases, the distribution becomes more normal. When the sample size is large enough, the distribution of a binomial variable is well approximated by the normal distribution. And for large sample sizes, note the approximate normality of the distribution of sample proportions. So for example, for n equals 100, the sample standard deviation, you can check that out with the figures on the spreadsheet, is very close to the population standard deviation, and the sample mean is very close to the population mean. In this instance, we're talking proportions. So we end up with this lovely result that when the sample size n is large, and usually it only needs to be, depending upon the distribution and the skew, 30 is sometimes good enough, large enough. The random variable for the sample proportion p hat has an approximately normal distribution with a mean mu equal to p and a standard deviation given by sigma, which is the square root of p on 1 minus p on n. Okay. Our last two demonstrations don't go for as long, so we should be finished up in about 10 minutes. So let's have a look at confidence intervals for proportions. So this is a pretty straightforward example. A survey found that 350 out of 500 people have brown eyes. Calculate and compare approximate 90%, 95%, and 99% confidence intervals for the proportion of people in Queensland who have brown eyes. The command we're going to use is the 1 proportion Z interval. I'm not going to use a calculator application, however. I'm going to use the notes application. So in a notes application, you can write text. So here you can see the text that I've written or typed in is in red. Then we've got some boxes, actually. If I click on them, they're boxes. They're called maths boxes. And we've assigned X to be 350, N to be 500, and the confidence level to be 0.9. Now, to insert a math box, all you need to do is press Menu, 3 for Insert, 1 or Enter for Maths box. And actually, when you come to do that and look at that again, notice that Control M is the shortcut. So press Escape, and I'll get rid of that math box. I'll need this math box. So you type inside the math box using the assign command each time, which is Control Symbols Template. I've assigned the number of successes, so the input is in blue. So X has been assigned to be 350. The output is in green, 350. Sample size N is 500. Input, output 500. Confidence level 0.9 in blue. Input, output 0.9. The beautiful thing about the notes application is everything that's essentially is housed in the calculator application is housed in here. So in a math box, if we press Menu, go to number 6 for calculations, and now this looks very similar to when you press Menu in a calculator application. Go to number 6 for statistics, number 6 for confidence intervals, and then number 5 for 1 proportion Z interval. Now, you can put numbers in, but because we've assigned X and N, what we can do is we can type in X, press Tab, N, press Tab, and this time we want the confidence level, and press OK. And so we've just found an approximate 90% confidence interval, and it's from 0.666 to 0.734, correct to 3 decimal places. Notice that P hat is 0.7. The margin of error, which we'll come to talk about in a moment, that's, if you like, the radius of the confidence interval, and N is equal to 500. So you're saying, well, why would we do this in the notes application? Well, what you can do is you can now click inside that math box representing the confidence level CL, change it to 0.95, and when you press enter, watch the output in green, it automatically updates. So now we've got an approximate 95% confidence interval of 0.660 to 0.740, correct to 3 decimal places. And again, change the confidence level to 0.99, and we get an approximate 99% confidence interval of 0.647 to 0.753, correct to 3 decimal places. Okay, so what have we just found? Well, they're the results we found from our 3 confidence intervals. And what we can conclude is being more confident means that a wider interval is required. And it's also really important to remember, we haven't got enough time to go through this tonight, but you can set up a lovely demonstration that there are variations in confidence intervals between samples, and that most, but not all, confidence intervals contain the population proportion P. So if we had 20 samples, we would expect the population proportion, if we had 20 confidence intervals at the 95% level, we would expect 19 of them to contain the population proportion. And on to our final example this evening is sample sizes and margins of error. So we're going to determine the sample size required to achieve a margin of error of 2% in an approximate 95% confidence interval for the population proportion P of people in Queensland who have brown eyes if the sample proportion P hat is 0.7. So the margin of error, which I've called ME, but here it's M, it's given by the particular Z score that we're related to, is related to, multiplied by the square root of p hat by 1 minus p hat on n. It's also, as I've mentioned, the radius of the confidence interval. So, for example, for a 95% confidence interval, you would substitute m equals 0.02, p hat is 0.7, and that value there, that comes from inv norm of 0.975. And then what you would do is you would solve that equation for n. And we can do that on a notes application. So it's a similar setup. The text is in red, math boxes, control M, inputs in blue, outputs in green. So here we've got a margin of error of 0.02, got a sample proportion this time p hat of 0.75, and we've got a confidence level of 0.99. And you may not have seen this before, but you can assign the thing that you want to solve for n in terms of a command. So the assign symbol again, control symbols template, n is assigned to be nsolve, which is numerical solve, and you get that in the usual way of 0.02, or m equals the inverse normal. In general, it's 1 plus the confidence level divided by 2, multiplied by the square root of p hat times 1 minus p hat on n, and solve for n. And so this is telling us that for a margin of error of 2% and a sample proportion of 0.75 and a confidence level of 99%, a sample size of 3,110 is required. And you can go back here and you can change that to 0.7. Change that to 0.95, and notice that you get the update. So in this instance, it would be 2000, around about 2016, 2017 people required for your sample size. So in conclusion, what I've tried to illustrate in the last 50 minutes or so is to embed into your teaching the idea of simulation, and to explore simulation, to show sampling from various distributions, to show that the sample proportion in itself is a random variable, and also how to show or how to use the notes application to solve a range of sort of common questions more quickly by using math boxes to change particular values and get outputs with great immediacy. So thanks very much for your attention, and now I hand it back to John Bayment for some closing remarks.
Thanks, Peter. That was a really informative webinar. I think you demonstrated some great resources that can also be found on the free TI-TRB booklets, which, as we know, you helped create. And they, I think you're right, the fantastic visuals of sampling and proportions, which can sometimes be lost, like that dryness of statistics, that is really important that students understand. And these can be created by a teacher ahead of time. Is fantastic. And how good is the notes page? I think that you demonstrated that really well, and how easy it is to change those numbers and make it dynamic. So thank you, Peter.
Thanks very much.
So just a reminder that our dedicated Queensland TI education page can be found at education.ti.com/Oz/QLD. And if you scroll to the bottom of the page, you'll find the downloadable teacher resource ebooks, one of which, the mathematical methods that Peter was using tonight. We're going to begin wrapping things up. So if you have any last minute questions, please try and get those asked. I know that Peter will endeavour to answer them in the chat window. But also, if not, he'll add them to the planning of future webinars. And when you leave the webinar tonight, a brief 4-question survey will automatically appear in your browser. Your feedback guides us as we plan future online events. We will listen to your feedback, and so we hope you share your thoughts in a post-webinar survey. And if you're watching live in the next 24 hours, you'll be emailed a link to the past PD events. And I also encourage you all to check out our student, or teacher for that matter, online courses on our very own TI dedicated YouTube channel. And sadly, really, that brings us to the end of our webinar. Thank you to Peter for everything you've shared with us. I really appreciate it. And I know that our viewers have from what the comments in the chat as well. So thank you, Peter.
Thank you very much, everybody. Fantastic. Thank you.
And thank you, everyone, like Peter said, for joining us tonight. And we hope to see you back online again soon. So goodbye for now. Thank you.
Yeah. Ciao for now.